Thank you for the opportunity to present our work we've done over the last year to understand correlates of protection from SARS-CoV-2 infection. This is perhaps relevant to an HIV community in that it's proved much quicker and easier to find a correlate for SARS-CoV-2 than for HIV, where we still struggle. Firstly, to declare no conflicts. Secondly, you might have noticed the title might have seemed a little unusual. To want to discuss immunology versus immunity. What do I mean by that? Well, whenever we're exposed to an infection or indeed any foreign agent, we make a variety of immune responses to that. And those might be mediated by B cells in the form of neutralizing or non-neutralizing antibodies, ADCC, or T cells, where we might elicit both CD4, CD8 responses, and some of them might be polyfunctional or more effective than others. And we're quite familiar with the concept that these particular responses have different effects on different infections. So, for example, antibody responses we use as a correlate of immunity for a variety of acute viral infections like influenza, measles, hepatitis B. We measure the antibody levels to know if someone's protected. On the other hand, for T cells, we have an assay to detect T cell responsiveness in tuberculosis. We also think that T cells are important for control of viral infections like chronic herpes virus infections, CMV, EBV, etc. So when presented with a new infection, we would really like to know which of these is most functional. And that's for two reasons. One is we'd like to know what predicts protection. How might we test if someone's immune? And if something predicts protection, it doesn't necessarily mean that it is the molecule that mediates protection. It could be that it's just well correlated with that. So a separate question is what mediates protection, and what might we want to optimize in a vaccine? And we might refer to the first one as a surrogate marker of immunity, and the second one as a mechanistic correlate of immunity. So when SARS-CoV-2 came along, it was clear that we needed such a correlate, but how to approach that. So what I'd like to talk about is the work that we've done really starting about this time last year. First of all, looking at historical approaches to identifying correlates using the example of influenza. Then to talk about the novel method for identifying a correlate for SARS-CoV-2 that we developed. And lastly, the sort of validation of that and the application of this correlate to predicting immunity. So firstly, protective titers in influenza virus infection. It's generally accepted that a hemagglutination inhibition titer is predictive of protection, and that a titer of about 1 in 40 will give you about 50% protection from infection with influenza virus. And I'd say a titer of 1 in 40 against the strain that is the infecting strain. So how did this number come about? Well, many studies over a number of years have been performed to measure antibody titers in a cohort of individuals where usually find there's a distribution in hemagglutination inhibition titers. And then to follow that cohort over time after they're exposed to infection. And in the case of influenza virus, this involves experimental infection in a laboratory, as well as following people for example, over a winter where there's been natural exposure in the community. Then at the end of that exposure period, to identify who's been protected and who's been infected. And it's generally found, for example, that if you look at the HAI titer, the people who got infected started with a lower hemagglutination inhibition titer than those that were protected. So then what we can do is do a bit of fitting to this and say, if we assume there's a gradient of risk, that at low antibodies you have high risk of infection, and at high antibodies you have protection and relatively low risk, we can fit a curve to this data to estimate the protection for any given neutralization level. And we can also estimate the IC50, which is where this 1 in 40 number comes from, the level of antibodies at which you get 50% protection from infection. So that was what was sort of done historically for flu. But this time last year, we had no longitudinal data on antibodies and risk. So although there had been phase 2 and phase 3 clinical trials. They didn't have the results for all the antibodies before the trial, so it wasn't possible to do this type of analysis. But what we did have at the time was the phase 2 immunogenicity studies from 7 different vaccines. And so for each of those, they had run neutralization assays and measured the neutralization titer in their particular assay for a given vaccine. And we also had the phase 3 efficacy studies, the matched phase 3 efficacy studies for those 7 vaccines. So we could say, this is what the antibody level is, and this is what the protection observed was. And so you can then try and answer the question, does neutralization predict protection? The major challenge right up front is that there's no standardized assay for measuring neutralizing antibody. So all 7 different phase 2 studies use different assays. So you can see here that the Moderna study used a PRNT80, Novavax and IC99, Pfizer, PRNT IC50. So as we've reviewed elsewhere, it's difficult to directly compare these numbers between assays because they're measuring somewhat different things. But fortunately, all of them had a normal convalescent control group in the study. Now, that's a little bit problematic because there was no consistent definition of what a convalescent subject was, how long after infection. But nonetheless, we could normalize all of the results, at least within the one assay, to the convalescent subjects studied in the same assay. So when you do that, you can then compare between different studies and assays. And in addition to this sort of challenge with normalization of the neutralization data, also the efficacy reported in the phase 3 studies, there were slightly different definitions of mild, moderate, and severe infection. Now, all of those limitations on sort of comparing between studies notwithstanding, this is what you get when you plot the normalized neutralization titer on the x-axis against the protective efficacy observed in the phase 3 trials. And you can see there's actually a very good correlation there. And Earl and colleagues later performed similar analysis and found the same result. So now we can say that neutralization is correlated with protection, with vaccine efficacy. But we can't necessarily use this very easily to predict what the efficacy of a new vaccine will be. What we need is a more mechanistic relationship. And so what we'd like is a protection curve that predicts for any neutralization titer what the level of protection would be. So just thinking about what this data means and how to interpret it. So for example, convalescent subjects, they're marked in blue on the left here. So they will, and shown schematically on the right, so they have a mean neutralization titer of 1 because everything was normalized to convalescence, and they have some distribution around that. They also observe about 89% protection from reinfection in people that have recently been exposed to infection. So a very simplistic approach would be to use a cutoff approach. So to say, okay, 89% protected, 11% were infected. So let's just find the neutralization titer, which would, separate the bottom 11% of most susceptible individuals. That would be one way of finding a threshold. But as I mentioned, we don't think it's sort of black and white that you're protected above this and susceptible below. There's probably some gradient, some point at which you have 10% protection, 50% or 90%. So we could try and fit a curve that would, where we had a total of 11% that were susceptible based on the different protection at different antibody titers. Now, the problem is if you do that just for one study, just for the convalescents, you have a trade-off between the IC50 and the slope of that curve. So you could sort of move it back and forwards. So you can't uniquely identify it. But as I mentioned, we had 7 different vaccine trials, and we also had the convalescent subjects. So here is sort of illustrating the approach of sort of saying for each, what was the distribution of antibody levels for each vaccine and what was the protection level? So for example, at the bottom left is the convalescent subjects. They have a mean neutralization titer of 1 because everything's standardized to them, and they have 11% infected. Up the top is a Moderna, has a mean neutralization titer about fourfold higher than convalescent, and it has much higher protection as well. So if we fit simultaneously across all of these 8 data sets, then we can estimate the IC50 and that sort of slope of protection with antibody level. And when we do that, we find that an antibody level equivalent to 20% of the convalescent titer, it mediates 50% protection from infection. And we think that's equivalent to about 54 international units per mil in our assays. So now what you can do is, you know, the relationship between protection and antibody level. So now we can say for any given mean neutralization titer in a vaccine trial and its distribution, we can predict what the efficacy would be. And on the right here, you can see the red line is the best fit of that function, and the shaded areas are 95% confidence intervals. But also in green, right in the middle there, you can see the results for Covaxin. They weren't actually fitted to the line. They came out after we'd done the analysis and fitted this curve. We had known in advance what the neutralization titer was, but the efficacy number came out in early March and fell almost exactly on our line, confirming in our minds that this functional relationship was actually useful at predicting vaccine efficacy. So everything I've talked about up to now has been based on the sort of primary outcomes of the phase 3 trials, which was protection against symptomatic SARS-CoV-2 infection. Now, in addition, they also looked at the frequency of severe SARS-CoV-2 infection. But because, even though the trials were very large with tens of thousands of individuals, there were less than 100 severe cases of SARS-CoV-2 identified across the combined trials. And in most trials, none of the vaccinated individuals actually had severe infection. So this is great for vaccine efficacy, not necessarily so great for trying to estimate protection against severe disease. But nonetheless, we can fit the same model for protection. Shown here, you can see the confidence intervals are substantially wider. And what we find is that whereas 20% of the convalescent antibody level was needed for protection against symptomatic, you only needed 3% of the convalescent antibody level for protection against severe disease, about 6-fold lower. So at the time, we didn't really have data on waning or efficacy against variants, but subsequently, this has turned out to provide a very good explanation of why protection against severe infection is maintained better over time than protection against symptomatic infection, and similarly why protection against severe infection is maintained against the variants even when protection against symptomatic infection is lost. So the first conclusion is that neutralizing antibody is a very good correlate of immunity to SARS-CoV-2 infection. And the mean neutralizing antibody titer of a vaccine can be used to predict its efficacy. I'll also mention that we think this is likely a mechanistic effect, that antibodies themselves are truly mechanistic in mediating protection, since passive antibody therapy has also been found to be protective against infection. So how do we go about validating the curve? Well, recently we've looked at how this data, which I'll sort of call the vaccine comparison data, where we sort of compare antibody levels and efficacy across different vaccines, how that works at the individual level using the flu model, the flu approach of looking at antibody levels of individuals. And secondly, how we use this to predict efficacy against the variants. So just to remind you that in the sort of individual, the model similar to flu, the idea is to measure antibody titers of individuals before they're exposed and then look at who got infected and what their initial antibody levels were. So in this case, the studies, there are a number of studies that were done on this. The first to come out was by Bergwerk and colleagues in Israel. And they studied Israeli healthcare workers that have been vaccinated with Pfizer. And what they found was that individuals who had breakthrough infection had a lower mean antibody titer than control individuals who didn't get infected. Similarly, Feng et al. Studied the AstraZeneca vaccine from the phase 3 trial of the AstraZeneca vaccine, measured antibody levels before infection and looked at who got infected. And Peter Gilbert in Seattle did the same for the Moderna trial. And this is great. You can see that each of these found similar relationship between between neutralization titer and protection. The Bergwerk paper didn't actually try and fit this model, but the other two did. But how do we know how that their curve lines up with ours? Because they used quite different assays. So unfortunately, they didn't have convalescent groups to sort of normalize things, but maybe even better than that, they actually had the titers of the vaccinees. So for example, we know that the FENG study, which is on the right here, used the phase 3 AstraZeneca trial data. So if we assume the mean neutralization titer of the, I've got my arrows going wrong here. Sorry, this should be going to the Chadox and the other one to the Moderna, but it'll excuse the mix-up. So with the phase 3 trials, as long as the mean neutralization titer in the phase 3 trials is the same as in the phase 2 trials we analyzed in the different assays, then we just normalize those means to be able to compare between the assays. And we can do that for each of the vaccines, Bergwerk for the Pfizer, FENG for the AstraZeneca, and Gilbert for the Moderna. And then we can plot all of that data. So here we've plotted it in two different ways. Firstly, taking the raw data for the neutralization titers of individuals who are infected and uninfected, and look at the risk at any given neutralization titer that someone was infected or protected. And that's these black dots. And you can see that they're sort of shaded according to how many individuals contributed to the number. So you can see that because we've got obviously a normal distribution in the center, we've got a lot of individuals and not many out at the sides. Then we can also look not for the Bergwerk, but for the other two studies about the protection curves that were estimated. So, for example, the red is the curve I've been showing you that we derived from the vaccine comparison study. The blue line is what Peter Gilbert arrived at from the study of the Moderna vaccine. You can see it disagrees a lot with our study at lower neutralization levels, and it also disagrees a lot about the IC50. So the IC50 for ours is about here and is a long way to the left. When you look, Feng et al. Studying the AstraZeneca vaccine, they use two different assays, a native virus assay and a pseudovirus assay. The native virus assay, the curve follows ours very closely. The pseudovirus assay, again, seems to overestimate the IC50 compared to what we saw. But in fitting these models, there was a limited range of neutralization titers for which there was data, because obviously the mean of the Moderna centers around 4 times convalescent, etc. So when you focus in on where there was sufficient data, you can see that both the estimates at the individual level of protection and the curves agree very well between these breakthrough infection studies and our vaccine comparison. So we found that very reassuring that we're actually measuring the same thing, comparing cross vaccines in these individual infection studies. So the next thing that we'd like to do is to be able to use this relationship to predict vaccine efficacy against new variants. For example, all of the vaccines studied in what I've talked about up to now have been using the ancestral spike, and all of the efficacy estimates are against the ancestral virus. But we know that we see a drop in neutralization titer to new variants because of immune escape. So if I vaccinate someone and have a certain titer against the ancestral virus, the homologous immunogen, I've got quite a different titer against the heterologous immunogen when a new variant comes in. So there's a major question of, can we still use this approach to predict vaccine efficacy against the variants? So, for example, this is a study we published last year where we tried to look at the average drop in neutralization titer to a given variant compared to the ancestral virus. We found there was quite a difference across different laboratories and assays. So we used the average of the available assays. In some cases, 9 different studies were averaged, in some cases just 1. But you can see here, for example, that the alpha variant has a drop in titer of about 1.6-fold, the beta about 8.8-fold, the delta, I guess most relevant just before Christmas, about 4-fold. So as I said, this is the drop in neutralization from the ancestral to the variant for someone who was vaccinated with the ancestral. And then when Omicron came around in December, we did a meta-analysis of 4 different studies of the drop in titer and found the drop of about 10-fold, probably around that or even slightly more. So it is the most escaped virus that we've seen, variant that we've seen so far. So what we need to do then is take our existing model, which is all ancestral versus ancestral, and scale it to look at these drop in neutralization titers to the variant. So the first approach, a first way to visualize this is to move the dots. So for example, here you can see on the left, all of these are the ancestral titers and efficacy, and they're now in gray in the background on the right. And the blue and orange and purple dots are the alpha, beta, and delta variants, and the predicted titers based on the drop in titer and the predicted efficacies of different vaccines. So, for example, up here is Novavax, has about 4-fold the average convalescent titer against ancestral virus. And if you look at the alpha variant, as I said, it drops about 2-fold. And here's the drop in neutralization titer, and there's the observed drop in efficacy. Similarly, if you look at the drop against the beta variant, again, a much higher drop now, 8-fold, and here's the observed efficacy. So you can see that the drop in titer and the drop in neutralization titer is clustering around this line. But another way to visualize it is to simply scale the curves rather than the dots. So you can look at the different variants individually. So on the left is the same curve I've been showing you, ancestral versus ancestral. And then we've got the curves shifting right for the alpha, delta, and beta variants. And the colored dots there are the observed efficacies with symptomatic infection on the top and severe infection on the bottom. Now, here we've got much wider confidence in 95% confidence intervals. And the reason is because we don't just use the uncertainty in the model, which is what's shown on the left. We also use the uncertainty in our estimate of the drop in neutralization titer, the uncertainty in the mean neutralization titer of the vaccine, et cetera. So we've got broader 95% confidence intervals. But what we observe is that of all of the sort of reported efficacies against the variants of concern, if we look at the lower 95% confidence interval, 13 of 14 studies have an efficacy above that. Or if we include the ancestral, 22 of 23 studies have an efficacy at or above the 95% confidence interval. So this gives us confidence that we can actually estimate the efficacy of vaccines against variants. More recently, and this was done just before our Christmas and summer vacation, we aggregated data on Omicron neutralization from several studies that had come out as preprints at that time to look at what the average drop was, as I said, about 10-fold, and then to predict efficacy for different vaccines. So this is just a summary of that, where you can see the model prediction for different vaccines. So here, is a predicted efficacy 4 months after vaccination, so allowing for waning immunity with the AstraZeneca or the Pfizer vaccine. And the triangles are the model predictions and the squares are the data. And here's the same 6 months after vaccination. And here is the predicted efficacy following boosting. So you can see that the model seems quite predictive of efficacy for these different vaccines. And obviously, we're very interested as more efficacy data comes out to look at that and confirm our findings. So what this means is that we think the model is very useful for predicting both the efficacy of new vaccines and the efficacy against new variants. So for example, for a new vaccine, if we can work out what its mean neutralization titer is, compared to the other vaccines or against ancestral, then we know where sort of on this axis we lie, and we get a prediction of what the efficacy will be. Similarly, if we have a new variant and we get a drop in neutralization titer to that variant, we can generate the sort of new curves predicting efficacy for that. So we think that this will be very useful going forward. So conclusions that the results of our vaccine comparison approach have been validated by a more traditional analysis of titers in breakthrough infection. Neutralizing titer predicts protection against new variants as well as the homologous vaccine virus strain. And it also accurately predicts waning immunity, which I don't really have time to present today. Future challenges are that all of this has been sort of considering people exposed to the ancestral immunogen. But now going forward, we're going to have people with a wide heterogeneity of exposure histories. So you might have got, infected with Delta and then vaccinated with the ancestral strain, or you might have been vaccinated with the ancestral strain and then infected with the Omicron. In those cases, we expect the cross-reactivity against any new variant could potentially be quite different. So we can't just rely on the drop in titer from the ancestral. We actually need to be able to measure the absolute titer to a given variant. And to do that, what we need is a standardized assay so we can compare between studies and also predict protection from new vaccines and new variants. We don't really seem to have much of a movement towards standardization of assays, but I think it's going to become essential in the next 12 months as we have this heterogeneity of exposure histories. So I'll leave it there and thank those that actually did the work, in particular, David Curry and Deborah Cromer in my group, who are two very, very talented postdocs and emerging leaders who contributed to the work. Also our collaborators at Sydney University, at University of Melbourne. Many of you will be familiar with Stephen Kent at WHO Flu Centre, and Alex Siegel in the Africa Health Research Institute, and our funders. And I'll leave it there. Thank you very much.